Sweet. Okay. So we'll give, another minute or so of people to mosey on in. What is this? Oh, it's a pencil. Black pencil. So we're going to talk about series today, and in some sense that, like, if sequences are functions, series are their integrals, right? That's sort of the idea. So you've got this sequence, and it's just a map from the naturals to the real numbers. And then a series is the sum of all the elements of those sequence, right? And that's the exact same sort of thing that, right, morally speaking, that is what an integral is, right? You just add up, all the parts of the function. So that's what we're going to be doing today. And in fact, it's more like an improper integral because, of course, we're not going to add up finitely many things. That's kind of boring. We all know how to add. The more interesting thing is going to be, well, how do we add up infinitely many things, right? Okay, so that's our goal. All right, so we're talking about series. And yeah, first thing right away, let's just go into a definition. So definition, so given a sequence, okay, and in this case, I'm actually going to write down what the indices are. Let's see, let's start at 0. For some from n equals 0 to infinity, the series associated to an is this thing. Okay, so right now this is just a purely formal object, right? Like we haven't talked about whether this thing is finite, really, even if it makes sense. And what it is going to be, I guess even maybe I should define this thing first. So we're going to define the partial sums of the series. So the partial sums of this series are Sn is the sum from k equals 0 to n, ak. Okay, so that's totally a thing. We know how that thing works, right? That's actually just a finite sum. So we can just add those things up. So the partial sums of the series are the Sn's, which form a sequence. Okay, so if you're given a sequence an, there's a corresponding sequence Sn, which is where you just add up all the first n terms of your sequence. Okay, so we'll say then that the series converges if the partial sums has a finite limit. So we say that the sum from k equals 0 to infinity, ak converges, right? Just like when we were talking about improper integrals, we could formally define an improper integral, but we still had to talk about whether or not it converges. So now we say it converges if this limit exists. In which case, we're going to say that's the value of the series. And maybe let me write this like this, just so that we can see the analogy between this and improper integrals. Right? So again, if we're thinking about the sequences being the functions, the sum as being the integral, then the series is the improper integral, right? It is the limit of all the finite sums. So it's the limit as you let the sums go off to infinity there. And yeah, that's how that's going to work. And I guess, yeah, so we say that it converges if this exists and it diverges otherwise. So if Sn does not converge, we say that the series diverges. Okay, very similar. And what we're going to see is there are lots of analogies between this and improper integrals as we go. So for example, we're going to have a basic comparison test. We're going to have a limit comparison test, but we're going to have a lot more tests than that. All right, so when we're doing improper integrals, those are basically it. Oh, we even have absolute convergence of the improper integral. We're going to have that for series as well. But for series, we are going to have a bunch more tests. There are a lot of tests. Now, well, actually here, these are notes. Let me maybe say this. So we'll say a couple of things here. So note. What do I want to actually say here? Yeah. So a couple of interesting notes for the partial sums. Like this. Okay. So the n plus first partial sum is the nth partial sum just plus the next term in the sequence, right? So normally, like even when you're talking about a sequence, there doesn't have to be any relationship between sequential terms. Sequential is maybe a bad word there. There doesn't have to be a relationship between adjacent terms of a sequence, right? But partial series, because they're defined via a sequence, you're guaranteed to always have this sort of relationship. So this is super useful, not only for computing partial sums, but it's going to be actually useful for proofs later. Okay, so this is very useful. For computing and proofs. Okay, so keep that in mind. All right, number two, these are not sums, okay? These are limits of sums. Is not a sum, right? And this is super important. So a lot of things that you see when people talk about series, and of course there's again all this sort of like nonsense on YouTube, and the point is that like people make the mistake of thinking, oh, these are, this is addition. We all know how to do addition. It's very straightforward. It's one of the first things that we learn mathematically is how to add, right? But these are not sums. These are limits of sums. And therefore we can't assume that the rules that hold for sums also hold for series. We can't make that assumption, okay? So we can't assume that properties of addition hold for series. All right. At least until we prove them. But the reality is that not every rule will hold. Okay. And in particular, the surprising one is in some sense commutativity of addition is going to fail. Okay. We cannot rearrange the terms of a series and necessarily get the same answer. So we all know, right? 1 plus 2 plus 3, that's equal to 6. And I can rearrange those terms, right? Because addition is commutative, I could write this as 2 plus 3 plus 1, or 2 plus 1 plus 3. I can rearrange the order of those terms however I like, and I'm guaranteed I'm going to get the same answer, right? That's commutativity. That's not true for series, right? And if you think about it, you see why. If you change the order of the terms, right? You're changing the sequence, right? You're changing which term corresponds to which index of the sequence. That changes your partial sums, right? And this is defined as being a limit of the partial sum. So you actually can change the limit of a series by changing around the order in which you do the addition. Okay, and that is maybe a little bit surprising. We'll see examples of this later. But here's the really crazy thing. So there is a result, and I'm trying to remember if we'll prove it. I'll make that, it'll be a game time decision. There will be a result which will tell us when we are allowed to do this, okay? It'll say, hey, if this property is true, then you can rearrange the terms of the sum however you like. But when you can't, okay, when rearranging the terms actually changes the value of the series, then you can actually rearrange them to make the series converge to whatever you want to. Okay, it turns out like that is true. If you get a series that is dependent on the order of its elements, then you can make it converge. You can rearrange it. You can find a rearrangement to make it converge to whatever you want, including diverge. right? So that's a little bit crazy. The proof is phenomenal. The proof is one of the coolest, and yet in some sense it's super obvious, but it's only super obvious as someone explains to you how it works. Because when you first look at the proof, you're like, what is going on here? But you know, if you stare at the proof long enough, you start to see what the idea is. So when that comes up, I'll give you an idea. I don't think we're going to prove that theorem. I'll give you a reference to look it up later, but this is called the Riemann rearrangement theorem. Yeah, maybe. I mean, like, it's a fairly, like, it's a named theorem, right? Like, it's significant. Again, it's intuitively obvious, I think, what's happening, but somebody should hold your hand when you go through it. So I'll kind of, when we get to it, if you maybe remind me, I'll give you an outline of how the proof goes. And I think many of you could be convinced that this is true and that if you did these steps, you'd be able to prove it, okay? So yeah, it's actually not that hard to prove, believe it or not. It seems like, if you try and think about it now, like, how the hell am I going to prove that? No, it turns out not to be that hard. But again, we have to learn what that condition is in order for things to make sense. Okay, the next thing. So integrals generally, in our experience, were pretty easy to find. We know that there are some functions that don't have elementary antiderivatives, and that's okay, but those seem to be relatively rare, right? In our experience, there were lots of functions for which we could find elementary antiderivatives. Turns out that's almost impossible for sums. So it's almost always impossible to find a closed form expression for the partial sums. Okay, and closed form here means like where you've taken the sum away, right? So that, you know, if I want to be able to evaluate what the 10th partial sum is, ideally I'd like to not have to add up the first 10 terms, right? It'd be really nice if I could find a formula which just gave me the nth partial sum without having to add them all up. So as a general rule, that's pretty much impossible. That's, in some sense, it's even worse than the case with integrals, right? And that's just because when you're dealing with discrete things and you're adding discrete numbers, you actually have sort of less tools to work with. So we will see a couple of examples in today's lecture of cases where we can do this, but as a general rule, this is very hard. As maybe like a super famous example, this series, so we got to start from 1 here. Okay, this seems like a really simple series, right? Like, it's very straightforward. It's just 1 plus a half plus a third plus a quarter and so on and so forth. It's a very straightforward series. This has no closed form expression for its partial sums, right? Like, what do we do? So closed form again means, here, let me give you an example. So some of you might have seen this. So the sum from k equals 1 to n of k is n times n plus 1 over 2, right? So like what this says is, if I plug in, you know, if I want, you know, when n is equal to 10 here, I don't actually have to add up the first 10 numbers, right? I don't have to do 1 plus 2 plus 3 dot, 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 plus 10. I can just plug n equals 10 into the right-hand side, right? And I get 55. So that's great, because if you actually ask me to add the first 10, you know, numbers, 1 plus 2 plus 3 plus 4, it might take me a second. You know, there's Gauss's trick that you can use for this. But it's so much easier. I can plug n equals 10 into the right-hand side very, very quickly, right? And get the answer immediately. So this is what I mean here. This is a closed form expression, right? You don't actually need to do the sum, as you've actually found a way of just writing down the answer without having to add. Okay, and then finally, as a bit of a note, and then we'll start playing with one of these things. As a final note is just going to be notation, so laziness. So when we're feeling lazy, which is all the time, right? So when we're feeling lazy, we'll write. So this is pretty common, right? Or you might put the k right underneath. So basically, when the indices are applied, just like with sequences, right? When the indices are applied, you might just drop them and you say, yeah, the sum over k. Sometimes we get really lazy as well, and we don't even write the k, right? Because again, like it's implied. If it's the only variable there, that's obviously, and it's the index of the sequence, that's obviously what you're summing over. So lots of the time we're very lazy about this, just in the same way that we kind of use the same notation for integrals, right? We might just write the integral of f, and that's that makes sense. So when the indices are well defined, as they should be with a sequence, right? Because the indices are part of the definition of a sequence. When those things are all well defined, we could be lazy and we just might write this, right? Usually, I think most people don't use the latter one too much. They at least like to sort of write down what the index says just to remind themselves if no one else. But it does happen. Okay, so just kind of keep an eye out for that. All right, so let's do an example. It's fairly extensive. So hopefully we'll get our, feet wet. There aren't too many of these you can do before they become really hard to do. So let's say find an expression. And again, normally this is impossible. For the partial sums. Now, also, when we talk about series, generally, we're not going to talk about this, like we won't explicitly describe the sequence. We'll just kind of describe it immediately by telling you what the series is. So, for example, like this. What do I want? 1, 2n squared plus 2n, right? And determine if this converges. Okay, so yeah, that might be a little bit hard to read. Let me write that. So that's 2n squared plus 2n. Okay. Now, the reality is, if you see the trick with this one, phenomenal. If you don't see the trick with it, don't give it away. The first problem-solving approach is legitimately just compute the first couple of partial sums and see if you see a pattern, right? Again, there is a trick to being able to identify exactly what to do with this one, but we might not be at that level of sophistication yet. And honestly, I don't care if you ever get to that level of sophistication because we're never going to compute things. So let's just do it the old-fashioned way. Let's compute a couple of the partial sums, see what we managed to get. Again, here, I'm going to really leverage, it's too far off the screen. I'm going to really leverage number 1 there, which is the nth partial sum is just an plus the previous partial sum, right? So we're really going to use that just to make our lives a little bit easy. So let's compute some partial sums. Sum of the SNs. Okay. Oh yeah, you're right. I'm going to do that a lot, but Adam, thank you. So this is sort of our caveat warning now. I am going to end up screwing up K and N all the time. I don't know why. I have done this literally forever. And, as long as I have ever had to do sums, I have made this mistake. So this is going to happen a ton, and you guys are going to have to point it out to me, right? It should hopefully not happen in a test, but if it does, point it out right away. I'll try and be more careful there, but definitely it's going to happen during lecture, right? So point it out if you see it. Okay, so the sum from k equal 1 to 1, 2k squared plus 2k. Okay, what is that? So it's just a single number. So it's going to be 1 over 2 plus 2, right? So it's just a quarter. Okay, cool. Good. Everybody double check my math as well. Okay, so the sum from 2 to 2, I'm only going to write this out this once, because then after this, I'm just going to write it in terms of the partial sums. 2k squared plus 2k. So this is what I really want to use here. So it's going to be S1 plus the k equals 2 term, right? So what is that going to be? So that's going to be 1 over 4, 8, 2, so 12. Is that right? So it's going to be 1/4 plus 1/12, which is 4/12, but I think it's actually going to be better to write that as 2/6. And if you didn't see that right away, like you might not see why I'm writing it as 2/6. Once I write S3, hopefully it'll be a bit more clear. I mean, again, I only know to do that because I worked this example out ahead of time, right? Oh no, I said I wasn't going to do this anymore. Okay, S2 plus, but I get a 3 in here, that's 18 plus 6, that's 1/24, I think. So we're going to get, oops, that's going to be 2/6 plus 1/24. So that's 8, so that's 9/24. So 3/8. Right? And maybe, you know, I think probably you guys see the pattern here, but maybe let me just do one more really, really quickly. So when I plug 4 into there, 16, 32, and 8 is 40. Right? So it's going to be 3/8 plus 1/40. So that's going to be 16/40, which I'm going to write as 4/10. So again, right, my goal here, the reason why, yeah, exactly. So I haven't reduced this, these fractions precisely because I'm looking for a pattern and precisely because I want a pattern in N, right? So I see, for example, S1 has the 1/4, S2 has 2/6, S3 has 3/8. So it certainly looks like, right? So claim, it certainly looks as though Sn is N divided by what? 2N plus 2? Yeah, exactly. So let's check that, right? So now, of course, how would you actually prove it? Well, you'd prove it by induction, right? So by induction, so the base case is done, right? We already did it. So the base case is done. Okay, so assuming this is true for N, let's prove for N plus 1. So suppose Sn is N over 2N plus 2. Now, and again, you can see this is sort of like built for induction, right? So we're going to take Sn plus 1. That's going to be Sn plus An plus 1. So immediately we can use our induction hypothesis. So we get N over 2N plus 2 plus, all right, so what are we going to get here? So we're going to get, it's 2N plus 1 squared plus 2N plus 1. Right? All right. So what I want to do, let's give everything a common denominator. So let's write this again here. Let me just write this like this, and then I'm going to factor out a 2N plus 1 from everything here. What is that going to give me? N plus 1 plus 1. So that gives me N plus 2. All right, let's give it a common denominator. And again, you don't have to wait for me, right? At this point, I'm just doing algebra. So you can get ahead of me if you really want. So I'm going to get N plus 1 plus 1 over 2 times N plus 1 times N plus 2. So what is that? N squared plus N plus 1. Did I do this again? Why am I suddenly worried? 2 plus 1. N plus 2. Let me just double check my work in here because I feel like I made a mistake. N over, you're right. Yeah, you're right. So I actually had to multiply by N plus 2, right? Thank you. Thank God Nicole is here to keep me on the path. So N plus, oh yeah, there we go. That's going to make a big difference. So that's going to give me N plus 1 squared, 2N plus 1, N plus 2. We're going to cancel out some N plus 1s. That's going to give me N plus 1 over 2N plus 4, or 2N plus 2, whatever. Let's maybe just write it like that, because that's how we've been writing it. And voila, right? That is what we said it would be. Okay, makes sense? So again, we kind of got lucky there, right? That everything does actually work out. The math isn't terrible. There's a little bit of work there. But again, we're seeing that like I am arithmetically challenged. Okay, so the problem asks us to find the partial sums. So we found the partial sums. Now we can see, hopefully this thing is actually going to converge, because we're going to get the sum from k equals 1 to infinity, 1 over 2, almost wrote n. This is going to be the limit as n goes to infinity, k equals 1 to n. Okay, we found an expression for this, right? So we can plug that in. So n plus 1 divided by 2n plus 4, and that's going to be 1/2, like so. Okay, so again, right, here is an example where we were able to find a closed form expression for the partial sums. Generally, this is really, really tough to do, but there we go. Yeah, 1/2. So, I mean, yeah, what we would do here is if you couldn't just see the answer, right? You'd multiply and divide by 1 over n. So you get 1 plus 1 over n, 2 plus 4 over n. And then anything with a 1 over n term goes to 0. So this just gives you 1 over 2. You could L'Hopital it, but like there's a little bit of work to do there. So what you would do is you'd say like, listen, let's look at the function x plus 1 over 2x plus 1, right? And then you could totally L'Hopital that if you want. And you'd say the function x plus 1 over 2x, or sorry, 2x plus 4. The function x plus 1 over 2x plus 4 converges to 1/2. Therefore, the sequence it induces must also converge to the same limit, right? Alternatively, if you want to do it directly, the trick is really just look, if you have a rational, it depends on what you mean, Chuyang. Like for this sort of limit, yeah, basically the trick is to look at the coefficients of the highest powers in the numerator and denominator. And if they're the same, then you just take the coefficients, right? So in this case, there's an n in the numerator, and in the denominator, I took 1/2. Generally, no. In terms of like finding, like here where I used induction to find this answer, it required that I had a guess for the closed form expression. And like I said, for the harmonic series, there isn't one. Okay, so you guys can try this. Okay, try adding 1 over n. Do the harmonic series. Really, you can do almost anything you want, but try this series, and because it looks like it should give up a closed form expression, right? Like this is really nice. Like this seems like this is a pretty simple thing. It should give up a closed form expression. The answer is it doesn't. There is no closed form expression for 1 over k. And like, that's, I think, surprising. And like I said, try it, write down a couple of other series if you want, and see if you can figure them out. Even doing this, like k, I don't know, I need to choose a different letter, k to the m for some power m. So you guys have probably seen a couple of this. I wrote down one here where m is equal to 1, right? The n times n plus 1 over 2. For k squared, there's a formula. It's like k times k plus 1 times k plus 2 divided by 6 or something like this. I don't remember what it is. For k to the power 4, it's the k equals 1 thing all squared, and so on and so forth. All of those have closed form expressions, but the derivation of those closed form expressions are nightmares as a general rule. They require the use of, which polynomial do I want? The Bernoulli polynomials, I think, is what you use to derive those. So like, and that requires some heavy math. Like I'm actually pretty sure most of you could do it, but as a general rule, the derivation of the closed forms for these things, which again are pretty easy and are well known, involves a lot of work. So it's really, really hard. Generally, there isn't going to be a pattern here. We got very lucky. Now, the reason this one gives a pattern, and the reason why I know it gives a pattern, is because I designed it to. And the thing that I'm hiding to you behind the scenes, does anyone see what this is? Like the trickier way of writing this down? All right, like this is how I made this problem. 1 over k squared, I don't think it has a closed form. Like we know what it converges to, but even that trick uses typically a thing, right? Yeah, Nicole, that's absolutely true. So we can do it as like, we can factor out the 2K, and then what can we do? Does anyone see like the trick to do once we do that? You guys probably learned how to do partial fractions, right? So if you do partial fractions on the decomposed thing, yeah, I'm not generally going to ask you to do this, but this is this. Okay. Like I said, I'm not going to ask you to do this. I don't care if you guys can figure this out. Maybe I will. Who knows? So anyway, you get this thing. What is that? Does anyone recognize that as being like a really nice series to compute? Why is that series really easy to compute? That's a telescoping series. Do you guys see that? Yeah, exactly. Anika, sorry, because I can speak faster than you can type, right? But exactly, this is a telescoping series, which means that its partial sums are really easy to compute, right? Because again, just like you remember, we were trying to prove that like monotone functions were integrable, and we picked up exactly all the sums, all the intermediate sums get canceled. So the only thing that survives is the very biggest term and the very smallest term, right? And that ends up making this very easy to compute. So if I'd written it like this, it's actually not crazy that, you know, this is going to be nice. But this is a special example of telescoping series. As a general rule, yes. If you have a telescoping series where the intermediate sums get canceled, you do probably have a closed form expression, right? Things are very nice like that. But right, this is a special, very special case. Generally, this isn't going to be true. There are some other surprising closed forms though. So there's a special kind of sequence that we're not going to talk about. Have you guys heard about recursive sequences? Sometimes, like if you've taken 102, I think they sometimes talk about recursive sequences in that class. Yeah, you guys have seen that? So you guys, like, here's a famous sequence, right? F1 is 1, F2 is 1, F3 is, or sorry, Fn plus 2 is Fn plus 1 plus Fn. Right, what sequence is this? Yeah, it's the Fibonacci sequence. Thank you. Do you guys know this thing has a closed form expression? Yeah, there is a formula for finding the like 100th Fibonacci term without having to find the first 99. You can just go straight to the answer. Not only involving square root, which is again surprising because everything is integers, right? But it involves the golden ratio. So the golden ratio shows up, right? So that's kind of like a super cool thing. If you guys haven't done that exercise, I think it's a fun one to do. Maybe I'll give it to you on an assignment and you guys can run through it. I think it is in my textbook. I think I did put it. Okay, yeah, in that case, then I'm not going to worry about it. But this is a fun little exercise. You can see the golden ratio come up because basically, like you just, there's a polynomial which shows up, which just immediately gives you the golden ratio. And then it's a simple inductive proof from there. So it's a really fun exercise. Yeah, I mean, give it a shot. You guys, you have all the tools to do it. Like, what do you need? You need the quadratic formula and you need induction. And if you have those two things, you can do this exercise. Like, it's not too bad. Okay, so give it a shot if you want. I always thought that was one of the coolest things. There's so many like really cool things you can do with the Fibonacci sequence that are really surprising, really, really surprising. Yeah, I mean, there's harder induction, Chang. So that will come one day, but you're right in the sense that like, I think probably students struggle with induction more than, right? Because people are just trying to figure it out. It feels a little bit weird to be like, if I prove these things, then I've proven it for all naturals. I think that takes a little bit of time to wrap your brain about, right? But once you've got it, it's like, it's not too bad, right? But yeah, give it a shot. I really suggest that you all try it. It's a really, really fun exercise. Yeah, what you're going to see later on even. So what? When you get into, you guys might not have done this in 240 yet, but sometimes you induct on the dimension of your vector space, right? Sometimes when you get to group theory, you'll like induct on the size of your sets sort of thing. So sometimes you start to do induction in really weird places. And it's a little bit surprising. So there are definitely weird. And then, yeah, sure. Yeah. Induction on graphs is totally a thing. And then there are different types of inductions. You guys have probably learned about strong induction versus standard induction. But if any of you go take CS classes, you'll learn, I don't even remember what they call their induction. What is the CS? Yeah, exactly, Mumba. Thank you. Yeah, it's structural induction. And then when you get into like higher level math, there's something called transfinite induction, which is a nice, fun, sort of crazy thing that you can do, right? Because the problem with, transfinite induction. So if you want, you can look it up. You need a little bit more understanding of like ordinals and cardinals, but there's something called transfinite induction as well, which is just fun to say. I really like to say it. There's a proof. Yeah, there's a proof that it works, right? So very quickly, because again, I mean, like, I think it is really easy to be like, why does it work? So basically it is the whole domino thing, right? So you prove P of 1 is true. And then you prove that P of n implies P of n plus 1, right? Well, so like, but here's what it is. So the claim is that if P of 1 is true and P of 1 is true, then P. Okay, I've written this really poorly. Okay, let me write it as a proper sentence, not the sort of like all over the place thing. So theorem, right? If P of 1 is true, write your base case, and P of n implies P of n plus 1 for all n. Then P of n is true for all n. Right? That's what induction is. Right? You prove the base case, and then the induction step is to prove that P of n implies P of n plus 1. And then the claim is, well, now P of n is true. Why? Well, because P of 1 is true, and that implies P of 2 is true, right? And then once you know that P of 2 is true, well, you prove that P of 2 implies P of 3. So P of 3 is now true, right? Now P of 3 is true, so that implies P of 4 is true, which implies P of 5 is true, which implies that P of 6 is true, and so on and so forth, right? And that's why induction works, right? Because you've just proved in general P of n implies P of n plus 1. And then this is why people talk about, this is effectively the proof. This is why people talk about it as being dominoes, right? When you prove P of n implies P of n plus 1, you've set up your nth domino to knock over your n plus first domino. And then the base case is you just pushing over the first domino, right? So you set up all your dominoes so that one knocks the other one over, and then you just hit one of them down, and then it knocks them all down after, right? Where knocking down here is proving it true. So this is why it works. Does that make sense? No. The proof is really just dominoes. Like legitimately, that's how, a lot of mathematicians, I think, internalize why this works, is that you just knock them down. And one of the important fallacies that people make when they're doing induction is people will say, eventually at some point you want to prove things about countably infinite sets. You know what I mean? Like, and induction will prove something for every natural number, but it won't prove something is true for a countably infinite number. Do you know what I mean? Like it won't prove something for Aleph naught. And you can see that if you follow this domino chain, the domino chain goes forever, but it will never hit Aleph naught, right? It'll never hit the first countable infinity. So you can't use induction to prove things about countable infinity. The best you can do is every natural number. What do you mean like on Q? Because Q is countable, but it's like, let me think about one of the theorems that I'm thinking of. Right, okay, so here's a theorem that is true if I recall. So suppose Sn is a collection, no, S is a bad choice because we're using it for partial sums here. So let's suppose Un is a countable collection of sets. Let's even just do N and N is a countable collection of sets. And F, let's say sets of real numbers. and F is some mat from R to R, right? Then this is true, right? Yeah, you can do induction on Q if you really want. It is possible. Okay, but so for example, here's a theorem that you all could be asked to prove, right? Like this feels like a Math 102 thing. It's not, this actually isn't hard. But what students will do is, so if I were to put a finite number here instead, right? If I put instead of infinity, maybe let me use a different color here. If instead of infinity, I put M's, this is an induction proof, right? You're like, listen, it works for U1 union U2, right? You prove it. And then you say, now inductively, let's, prove it in general. But you'll ask students to do this and they'll be like, oh, look, I proved it that it works by induction for any finite number. Therefore, this result is true as well. And you say, well, no, actually, induction can't get this far, right? Like induction will work for any finite number, any finite union of sets. But this is strictly an infinite number of sets, and induction won't reach this. Does that make sense, everyone? Like why you can't use induction to prove this? Because it's infinity, right? It truly is infinity. And it doesn't matter how far you go down this chain, you'll never hit infinity. You'll only ever hit finite natural numbers. So this is sort of like a common fallacy that we do see amongst students. Okay? Is everyone okay? I hope I didn't like hurt too many brains. But anyway, so the way you can do induction on basically on any totally ordered set. The reason why you can do induction on Q, on the rationals, is because you have, like, it's a little bit tricky, but basically what you can do is if you can, like, Q is countable, and so it has the same cardinality as the naturals. Therefore, you can just map the rationals to the naturals and induct over the naturals in that way. Now, there's no guarantee that's actually useful for you, right? Because you still need some way of transitioning from one rational to the next. And as a general rule, that's going to be pretty tough, but it theoretically is possible, right? Theoretically, you could do it that way. Yes, there is. That's what transfinite induction is, right? Right. If we think about the word transfinite induction means, it means I've gone past the finite point, right? And this now allows me to inductively prove things on infinite sets. So that's what transfinite induction is actually going to give to you. Yeah, absolutely, Adam. Yeah. Yeah. Or make sure you get 0 in there somehow, right? Like depending on what your ends are. But yes, absolutely. You can prove something on all naturals by proving it holds when you go up the natural the integers and when you go down the integers. And yeah, exactly, right? Your kind of hypothesis here is just an extension, I think, of the proof of the fact that induction works. Or another thing that you can do is you can sometimes it makes more sense to, like, if you're trying to prove something on the naturals, to prove it for the even naturals and the odd naturals separately. Sometimes that makes sense, right? You prove P of 2 implies P of 4 implies P of 6, then you prove P of 1 implies P of 3 implies P of 5, and you can prove it for all naturals that way. The idea is that you just want to set up these chains that eventually hit everything, right? And so like you said, if you want to do the integers, you just set you have like 2 separate domino chains, and then you just kind of knock them both over, right? And whether you do that separately by knocking over 0 and then -1 and then +1, or if you can find a way to just knock over 0 and have it start both chains, both of those are totally fine. Yeah, your goal here is just to cover everything by a chain of implications. And if you manage to do that, you can prove everything. But you can see, yeah, exactly. Yeah, you could do this for Q. The problem with Q is figuring out what the next rational number is. And it is possible to define a next natural number because Q is countable. But again, it's usually not doable in a useful way, right? Because your next natural number might be a jump, right? And then you have to like jump back and then jump forward again, jump back and jump forward again. And depending on what you're trying to prove, that might not actually be a useful way of doing it. So theoretically, you can induct on Q. It's just, it's tough, right? It's usually quite nasty. Okay, I'm going to do a quick little theorem here, and then we'll probably go on break. But I think you all know this theorem. I don't think this theorem is crazy. So the theorem is the following. So the geometric series, but we're going to use this a lot. So the geometric series, the sum from k equals 0. 0 is important here. R to the k converges if and only if the absolute value of R is strictly less than 1. Okay, and in that case, the value of the sum is 1 over 1 minus R. So yeah, I think you've all probably seen this, right? This is a high school thing. Yeah, you might not have seen the proof. I think probably depending on, your high school, you might have just seen this stated, but like, we're going to do the proof. The proof is surprisingly easy. Now, again, like I can't overemphasize how useful this is going to be. Like this, the geometric series, even though we're like, okay, sure, fine, whatever, it's nice. I believe that even it shows up in real life. And of course it does, because it shows up in like compounding interest and annuities and things like this. But even for our purposes, theoretically, this is one of the most important series, I should say, not sequences. This is one of the most important series, because when you're trying to prove that things converge, one of the easiest things to compare it to is the geometric series, right? So again, we're going to learn some comparison tests, which allow us to determine when things converge. And a lot of the time, the geometric series is what we're going to compare against. Okay. All right. So the trick to this is, first of all, we need to figure out a formula, right? Just like we did for the example above, we need a formula for the partial sums. And that is actually going to hold regardless of R. So the absolute value of R does not need to be less than 1 for this part to be true. Okay, so proof. So first, let's find a formula for the partial sums. A formula for the partial sums. And let's give them a name. Let's maybe call it Sn sum from k equals 0 to n rk. Okay, and now normally I'm very comfortable using sigma notation. I do want to write this one out though, just so you can kind of see again what's going on. Right, that's what the partial sum, right? That's the series that we're talking about. Now the trick here is to multiply by 1 minus R. Okay, and I'm going to write this out in a special way just to help you see what happens, but I think you all could work this out, but something really cool happens here, right? So if we do 1 minus R times Sn, okay, so let me write out the 1 part. So we're getting 1 plus R squared plus, maybe let me add a couple more terms. So that's the 1, right? Now I'm going to multiply the R in. And this is what we get. Okay, and again, I've very kind of like suggestively written them sort of stacked on top of each other so that you can see that, yeah, you end up getting a telescoping series again. And when you do all of that, you just get 1 minus R to the n plus 1, right? And again, this isn't necessarily crazy. We know this is true, and I'll show you what I mean by this in a second. But we know that this is what happens when you factor, a difference of nth powers. Okay. So again, maybe let me put this as maybe just an aside here. So we know right, if we think of these as a difference of powers, that you can factor a 1 minus R out of that, and the thing that you're left over with is that. right? We've used this fact plenty. So that's effectively just what I'm rederiving is this fact. I guess I could have stated it directly from here, but either way, regardless of whichever of these things makes you, see this relationship, this allows us to solve for the sum. Like that. Yeah, exactly. So again, I imagine you guys saw something like that in high school, right? I think, the closed form expression for a finite geometric series is a well-known thing. And now, if we want to take an infinite geometric series, we're just going to take a limit as n goes to infinity, right? So hence, the sum from k equals 0 to infinity of r to the k is the limit as n goes to infinity. Okay, and at this point, I am going to yeah, exactly. Yeah. So this limit is going to exist precisely when r to the n plus 1 goes to 0. Exists precisely when the limit as n goes to infinity, r to the n plus 1 has to be equal to 0. That means that the absolute value of r has to be less than 1. Which occurs if and only if the absolute value of r is less than 1. And in that case, right, the r to the n plus 1 term goes to 0, gives us our answer. Right? So I don't think we've maybe said this part explicitly, but if you stare at it for a bit, you can probably convince yourself that this is true. Okay, like that the only way that this thing is actually going to converge to 0. So first of all, yeah, because if the absolute value of r is less than 1, this thing actually diverges, right? Like this will go off to infinity because you're taking numbers bigger than 1 and you're exponentiating them. And we know if you take numbers bigger than 1 or bigger than 1 in absolute value and you exponentiate them, they explode. And if you take numbers less than 1 and exponentiate them, then they shrink off and they go to 0. So you might need to convince yourself a little bit more of that. I don't think we said this explicitly, but just convince yourself that this is true. And you'll make your life really straightforward, really easy. And again, if you want to prove this formally without using functions of real numbers, use the monotone convergence theorem, right? Like r to the k, if r is less than 1, is going to be non-increasing. It's actually going to be strictly decreasing and bounded from below. And if you want to prove, and then basically that's actually it, because then when you take the reciprocal, you can get that it's going to diverge. But I'll leave that for you to sort out. It's not a tricky exercise. Okay, so yeah, we're going to use geometric series a ton. We need to be comfortable with it converging. All right. And let me just think about what I want to talk about next. Yeah, actually, we could stop there for now. That's a nice little breaking point. So that's about it in terms of examples, though, of sequences, at least until we get a little bit more tools that we can work with. So we're going to take a 10-minute break. When we come back, we're just going to start proving theorems on sequences, right? So we're going to prove the limit laws, for example, which is kind of boring, but yeah, we'll do it really quick. We'll generalize what we're going to do is we're going to take all those theorems that we have about sequences, and we're going to generalize them to series as well, right? Because remember, a partial, an infinite series, is just a sequence of its partial sums. So all the theorems that we have for sequences and convergence of sequences, we can also then extend to theorems about convergence of series, right? So some of it's going to be that, we're going to extend the monotone convergence theorem, for example. Okay, so we'll do that. Let's take a 10-minute break first, though. I've got about 10:03, 10:04 by my watch, so let's come back around 10:14, and then yeah, we'll prove all the results about series. Okay, so I'll see you all in 10 minutes. Go get some coffee and some food or something. See you in a bit. Okay, we're back. It's about 10:14 in like 10 seconds or something. All right, what do we want to do? We're just going to prove a bunch of theorems. For the most part, at the beginning, it's just going to be basic theorems, things like, oh, if you add two convergent series together, they're both convergent, sort of thing. And then I don't know if we're going to get to the beginning of the comparison tests today, but basically the same comparison tests that we talked about for improper integrals are going to be true as well. So if you don't manage to, if we don't manage to get to that today, one thing that you could do is try and state and prove them yourselves, right? Like that'd be a really cool thing to do. Okay, so let's see. What do we want to do? So the first thing is sort of like, again, your basic limit laws. So let's state the following theorem. And maybe I'll prove one really quickly, just to give you an idea how they work. Okay, so it goes like this. So suppose k equals 0 to infinity a k equals L. And the sum from, should I use a different index? Yeah, let's use n now. Yeah, don't use L. Let's use little l. Are both convergent. Okay, so the series that you get by taking the sum of these two things is also convergent and has exactly the limit you think it should be. Okay, and I'm stating this in a slightly weird way because I'm stating like, hey, it's equal to this number and is convergent. What I'm trying to do here when I do this though is try and emphasize that there's really two results that are happening here. One is that the series converges, and the second is that it converges to the sum of the two series, right? So again, there's always this, it converges and what the value of the thing is. So it does probably look a little bit weird, but hopefully you understand what I'm saying. And if you want to, you can expand it out, maybe include that as a note yourself. And then the other thing, maybe we should use no, let's use a C for this. So C AK is CL is convergent. I guess I didn't actually need to give them names like L and M. I could have just rewritten the series, but whatever. Right? So does that make sense? Does everyone see what I'm saying? Right? Sum of convergent series is convergent, and any scalar multiple of a convergent series is convergent. And again, the proof is super straightforward, right? It's literally just the limit laws. So I'm only going to prove one, and I'll prove it very quickly. I'm going to let capital A and capital B be the partial sums of each of these series. So let's let AN k equals 0 to n AK and B be the sum. BK, so that the sum from k equals 0 to infinity AK plus BK is the limit as n goes to infinity 0 to n AK plus BK. Yeah, exactly. It's linearity of convergent series. So if you want to call it that instead of the limit laws, like that's totally okay. Because in some sense, you might say like, well, we don't have a multiplication limit law. And that's true, right? We don't. And so like anything, right? It's, again, like I said, we don't know that what's true about, we don't know that the properties of addition carry over to the properties of a limit or of infinite series. But what we can often do is in processing the actual limit, we can reduce to a finite case as we've done here. So here, now that I've written this as the limit as n goes to infinity of the sum of AK to BK, well, the sum is finite. So this does obey the normal properties of addition, and we can split this up, right? And again, I guess I didn't even need to define the partial sums if I didn't want to. I probably could have. I could have just done this. And now by the limit laws, right, because both of these things exist, I can split this up into like the limit of, I'm sort of angry at myself for just not choosing a convention and sticking with it. Like, am I doing partial sums or am I just writing them out explicitly? What are you doing, Tyler? What are you doing? Well, whatever. It's the only proof I'm doing, so I can write it out kind of fully like that, right? Yeah, I'll take your word for it. I wasn't there. But again, critically, we needed that the limits converged, right? Remember, the limit laws require that your limits exist, right? So in order to do this, I did need that the limits existed in the first place. And then 2 is exactly the same, right? Just instead of adding, you're doing scalar multiplication. And so it's nothing big. But actually, what you are kind of seeing, if we want to talk about sort of its relationship to linear algebra, yeah, the collection of convergent infinite series is a vector space, right? In fact, just the collection of sequences, you all probably agree. So the collection of sequences are a vector space, right? Because you can certainly add sequences. The collection of, and you're not even worried about whether they're converging or not. The collection of convergent sequences is a vector space. The collection of sequences which converge to 0 is also a vector space. These are all subspaces of another, right? So all sequences is a vector space. Sequences which converge are a subspace. Sequences which converge to 0 are a subspace of that. All right, so these are all examples of infinite dimensional vector spaces. And then same sort of thing for convergent series, because really convergent series are just special examples of convergent sequences, right? So there's actually a lot of vector space stuff going on here. It breaks in the sense that you can't say anything, but you don't know. So like as sort of a silly example, like what if I took, the sum of k from k equals 1 to infinity, right? Clearly divergent, but you don't know anything. So if I added it to itself, it's still clearly divergent, but I could also add it to this, which is also, if you take negative k, that's still a divergent series, but when you add these together, you suddenly get a convergent series, right? Or maybe if I added it to that's a divergent series, but when I add them together, I get something which converges and converges to something non-zero, right? So just the point is that if one of the series diverges, you don't know. You have no clue what's going on. There's some could converge, there's some could diverge. There's just, you can't say anything without knowing more about the sequences themselves. So you just don't have the power to say anything like that. Divergent plus convergent is divergent. This is an interesting question. I'm inclined to say yes on the basis of a theorem that we're going to prove here in a second, which is basically, and somebody, I don't remember who exactly it was, somebody had this suspicion. Actually, we might as well just prove it now then. So someone, let me address your question. Let me do this one first. So I'm going to say theorem. So if the sum from k equals 0 to infinity, ak converges, then this is true. Okay. So if the series converges, then the sequence must go to 0. And hopefully remember, somebody asked this about improper integrals, and it wasn't true in the case of improper integrals, but it is true in the case of sequences and series, precisely because we just don't have, right? Remember, integrals didn't care about measure 0 sets, and that allowed us to do some sort of bad things with the functions. But series care about every element of their sequence, right? Every element of their sequence does actually contribute to the sum. So in this case, we actually do get this result being true, even though this one wasn't true in the case of improper integrals, right? And I think actually explicitly, I asked you this question on your last term test for improper integrals, right? Which was kind of a freebie because we did it in class. But anyway, in this case, we do actually get the result to be true. Now, in practice, this is sort of nice to know, but in practice, you usually use the contrapositive of this result, which is if you're trying to determine if a series converges, if the sequence doesn't go to zero, you automatically know that the series doesn't converge, right? The contrapositive of the statement in practice is often more useful. But the proof of this is really, really slick, right? And the proof of it goes like this. So recall that if Sn, and at some point here, I'm going to stop writing this out and I'm just going to say Sn is the nth partial sum or whatever. So if Sn is the nth partial sum, then an plus 1 is Sn plus 1 minus Sn. Okay, and I say recall because this is the first note that I wrote above, right? As soon as I defined what an infinite series was, it was the first thing I put in green. Recall Sn plus 1 is equal to Sn plus An plus 1. So I've rearranged that equation a little bit, but it's the same equation, right? And now I'm done. So the limit as n goes to infinity, and this is going to probably feel a little bit shady to you. But these are basically what I'm doing is I'm thinking of these as now being two different sequences. Even though they're very similar and very strongly related, Sn plus 1 is the series Sn, but I've just shifted everything up 1. So if I think about these as being two separate sequences, they both converge, so I can limit law them. And they both converge to the same thing, right? Because they're effectively the same sequence, just one is shifted a little bit from the other. So I get 0. And I'm done. So I think the first time you see that, you're just like, hold on, this can't be legal, but 100% it is, right? And if you really want to be super rigorous about it, all you say is, let's call Sn plus 1 a different sequence, right? It's the sequence Sn, but we've just added 1 to every single index, right? And that's totally okay. And then convince yourself that if you add 1 to the index of a convergent sequence, it's still convergent. Like obviously you didn't change anything, right? And now, Salman, for your question, what I would say is the following. I would hypothesize that the answer is yes, that convergent plus divergent will diverge. And basically what you want to show is, what do I want to say? Well, if you diverge, we can't guarantee. Yeah, okay, how would we prove this one? This is an interesting question. So if it diverges because it goes to infinity, great, but that's not enough, right? So if it diverges because it's unbounded, that's not a problem. The thing that I'm worried about is the series like plus 1, minus 1, plus 1, minus 1, plus 1, minus 1, right? That doesn't converge, but it doesn't go off to infinity either. So what do we want to do? So basically, yeah, okay, here's what you want to do. So for like you choose an epsilon band, right? For your new convergent, you've got your divergent plus your convergent series. So you choose an epsilon band. Now for your convergent series, you know that if you go far enough, you're going to be within that epsilon band. But your divergent series will be guaranteed to leave it, right? So knowing that your convergent series has to go to 0, you should be able to squeeze it into a narrow enough epsilon band that the divergent series, that basically when you add it to the divergent series, it doesn't really do much. You know what I mean? Like the convergent sequence doesn't contribute a lot to the sum. Do you know what I'm saying? Like the convergent thing only contributes, some epsilon over 10 term or whatever to the sum. So the sum of the divergent and the convergent series is dominated by the divergent one. And you should be able to use that to prove that you always leave an epsilon band. Yeah. So write that out. I think that's sort of like an interesting, sort of clever hypothesis that you have. And that's how I personally would prove it, is that if you go far enough down into the into the index, because I am guaranteed that the convergent series has a sequence which goes to 0, eventually, the contributions of the convergent series are very little, and your sum is dominated by the divergent thing, which should break. So I think the theorem is true, and that's how I would prove it. That would be my first approach, at least. Yeah, so prove it. I would love to see that, if you can write it out. Like I said, I don't think it should be too bad. Probably going to need some sort of like epsilon over 2 thing here, but I think it should be doable. Okay, so there's that. So what have we proved? We've proved like linearity. We've proved that this thing goes to 0. And like I said, the main way that you would use this theorem that we just proved is actually to prove that series don't exist, right? Or don't converge. Because if the sequence doesn't go to 0, the series doesn't converge, right? Okay. And again, like in practice, we're really actually not even going to do that much. You can imagine the ones I'm going to give you are going to be the ones where it's more interesting. A natural question for this, by the way, is whether the converse holds, right? Does anyone know? Is this an if and only if in secret, and I just haven't proved the opposite direction because we don't have the tools yet? I don't know how, if compact is necessarily what we want. And Yvonne is guessing no. Okay, here. So let me just state it right now. We might get to the proof today. So note, the converse does not hold. Right, so what would the converse say? And exactly, yeah, the harmonic series does not converge. Okay, actually, are we in a position to prove this? I think we could. Actually, I want to prove the next thing first. Maybe let's prove the next thing, and then that should lend into the proof of this. So I'll prove that the harmonic series does not converge for you. There's so many proofs that the harmonic series doesn't converge. It's actually it's a really cool thing just to see how many you can come up with. My book has one. I'm actually going to use a slightly different one than the one in my book, but I'll tell you how the one in my book works because I love that one. It's one of my favorites. But okay, here's another theorem. This is basically the monotone convergence theorem. Now, this isn't a standard name. So if you talked about the monotone convergence theorem for series, you wouldn't find anything. But it is the monotone convergence theorem. And let me show it to you. So it says if AK is greater than or equal to 0 for all K, and there exists an M in R such that it could be M greater than 0, it doesn't matter, such that the sum, i.e. the partial sums, for any n, then the series converges. Okay. And if you've internalized what the monotone convergence theorem is saying, right? Remember, what does monotone convergence theorem say? It says, if I give you a sequence, a non-decreasing sequence, which is bounded from above, then you converge. So the guarantee that AK is greater than or equal to 0, that stipulation ensures that the partial sequences of my series are non-decreasing, right? And then this M is the bound from above. Those things are going to guarantee that we converge, right? So the proof of this is really just MCT. So proof. So claim 1, or maybe let's say let Sn be the partial sequences, partial series, be the partial sums. right? Claim one. Sn is non-decreasing, right? Indeed, Sn plus 1 minus Sn is equal to An plus 1, which is greater than or equal to 0. So Sn plus 1 is greater than or equal to Sn. Right? If you just keep on adding positive things, your sum must be getting bigger, right? And the same sort of thing was true for integrals as well, right? If your function was always strictly greater than 0, then your antiderivative was an increasing function, right? We know that that's true. Claim 2. The sequence Sn is bounded from above. And indeed, you know, Sn is less than or equal to m for all n by assumption. So hopefully you see why this is just the monotone convergence theorem, right? Just the hypotheses of the theorem are exactly what we needed in order to apply the MCT. So by the MCT, Sn converges. And if the partial sums converge, that means that the infinite series converges. Right, and we're done. Okay. So what do I want here? Yeah, I guess that actually, okay, yeah, let's prove the harmonic series diverges. I guess I'm actually not going to use either of these two theorems, but I'm going to prove that it goes to infinity. Okay, so let's do that. Let's actually state this as a theorem, because this is one of the most important results that we can do. So the series diverges. Okay, so our claim is that this is actually infinity. Okay, that this, like, it is unbounded. It becomes as large as you want it to be, right? So let Sn be the partial sums. We claim that the partial sums go to infinity. Now, I guess we haven't strictly defined what it means for a sequence to go to infinity, but it's the usual thing, right? It's for every m greater than 0, there exists an n in n, such that for every n greater than n, right? Which is exactly our definition of, you know, a limit going off to infinity that we had from functions, right? So if you go far enough, you're always above some bound. So I'm going to prove this. And if you go to infinity, you certainly can't go to a finite number. Proof I'm going to use is actually one of your homework problems that you guys did. I think it was assignment 10. You correct me if I'm wrong. So recall, plus 1 over k. You remember proving that? Good. And the right-hand side is basically the harmonic series, right? So log k plus 1 is greater than sk. Okay. Now we know that log goes to infinity, right? So since the limit as k goes to infinity of log k is equal to infinity, well, here, let me maybe phrase this slightly different way. So let's say now, right, we actually want to prove this definition. So let's say let m greater than 0 be given. Since log goes to infinity, right, just because we know the function log x goes to infinity. So that tells us log k goes to infinity. There exists some natural number n such that if n is greater than n, that implies log k is bigger than m. Thus, is that what I want? Yes. Thus sk. Wait, did I do this backwards? Is log k, no, log k is less than this. All right, hold on, let me draw it out. Somebody double check my sign here. So we've got 1, we've got like 2, we've got 3. We use the lower bound, right? So we get that log of 3 is actually going to be bigger than 1/2 plus 1/3, right? So did I get these? Damn, did I use the wrong one? Because I want that sk is actually bigger than this. Damn it. Okay. It's greater than? Okay, so I used the wrong one then, right? Because I need the other direction. I'm trying to show that sk is bigger than log k. So the other one went to, it was actually, sorry about this. So I want, right? Because I think in assignment 10, there were 2 sides to that inequality, right? And it's just depending on whether you use the upper or lower Darboux sum. Right, and then this will work. So thus, if n is bigger than n, we have Sn is less than log n plus 1 over n, which is less than, no, sorry, greater than, what am I doing? Which is greater than n. There we go. Right? So it goes off to infinity. Sorry, I screwed up the direction of that. That's my bad. That's what happens when you're just like, oh yeah, I can prove it on the fly. I don't need to work that out ahead of time. So important lesson. Don't do that if you ever have to teach. Okay. Did I get my inequalities right? Somebody please tell me if I screwed that up again. I really hope I didn't, but okay, I'm just going to pull up the assignment and just make sure. But log is, yeah, we want log to be less than, right? So I need to take the upper sum instead of the lower sum. Like that. All right. So you can see log 3 is actually less than 1 plus 1/2. Yeah, I think that's the right direction. Okay, does that make sense? Are there any questions about that? I'm happy to answer questions about that because I screwed up the inequality at the beginning. So please stare at that and make sure it makes sense. But basically, 1 over n and log are really closely related to each other, right? We know that in some sense, the sum of like the harmonic series is basically an approximation to log, right? If I take two adjacent terms of the harmonic series, log is somewhere in between them. So that's why these two things are closely related. And in particular, then what I can guarantee is that the harmonic series is always greater than log, but log itself diverges. So that must mean that the harmonic series itself also diverges. So is that okay? Is everyone all right? I'm not getting a lot of affirmation here, but I will take the lack of, okay, sweet. That's good. That's affirmation. I'm happy. Okay, so that's that. And again, this is surprising. So if any of you get a chance, what you should try and do is go and ask Wolfram Alpha how, like, here's a question. Somebody go plug this into Wolfram Alpha for me. It's a question. For what, like, what's the first value of n? Such that this is true. Okay, because we just said the series goes to infinity, right? It explodes, it gets arbitrarily big. What's the first value of n such that this is true? What does Wolfram Alpha tell you? So if we ask Wolfram Alpha here, hopefully you're faster than me, but let's see what Wolfram Alpha says. Okay, that's a crazy, I don't even know what the hell number that is. The harmonic number. Sure. Thanks, Wolfram Alpha. You're so useful. Does anyone get a number? So nobody knows? Thank you. Yes. So anyway, but okay, based off our approximation here, what would you guess the answer is? Like, look at what log is, right? Log is an approximation to the harmonic series. So what number do you roughly think this is true for? It should be about e to 100, right? It should be about right? That's a crazy number, right? E to the power of 100 is insanely big. How many digits does e to the 100 have? Do we think Wolfram Alpha could at least do that? Come on, Wolfram Alpha, stop letting me down here. So it's about 2.7 times 10 to the power of 43. Right? That's how long it takes for the harmonic series to break the number 100. So to say that this is a very slow growing series is an understatement, right? It goes off to infinity, but you require, what is that? The number of atoms in the universe? How many atoms are in the universe? Yeah, Wolfram Alpha, what do you say? Okay, that's 10 to the 79. So there are more atoms in the universe than that, but still, right? There are, like, that is a stupid number just for the harmonic series to break 100. So it does go to infinity, but it goes really, really slow. So do you get an approximation? Like, does that make sense? Like, if you were to graph this thing, it looks like it might converge, right? Because it goes so slowly, you can't even tell that it's actually forever increasing, right? Like, it's never going to taper off. It's always getting bigger, but it takes forever for it to grow. It is so slow, right? So slow. So yeah. Okay, there's a slicker proof. Maybe I'm not going to start the convergence theorems. I don't think I want to start that. I've thrown a lot at you today. I want to show you the really slick proof, though, of this fact that doesn't use our homework problem and doesn't involve me having to use inequalities. Maybe it does. Okay, here it is. I'm just going to wave. I'm going to hand wave it a little bit. I'm going to let you do the details. But again, this is the one that I do in my book. So if you have someone, if you know someone who knows the book proof, you can have them look it up. And this is a fairly standard proof as well. So let me just write it out. Let me get a hand. I'm going to hand wave it. So alternatively. Okay, so we've got 1 plus 1/2 plus 1/3 plus. I need to write out a bunch of terms so you can see what's happening. Plus dot, dot, dot. Okay, so here's what you do. What you do is you say, I'm going to group them like this. Maybe actually let me sort of write out the next terms. 1/9 plus dot, dot, dot plus. Okay, so you're going to group terms like this. So do you kind of see the pattern? So here are 2 terms. Here there are 4 terms. Here there are 8 terms. Okay, so starting with the 3rd element of the sequence, I'm going to start grouping them into, the powers of 2. And then what I'm going to do is I'm going to say, look at the smallest number in each grouping. So I guess I do have to use inequalities here. This is going to be greater than 1 plus 1/2. And now I'm going to replace every element in its group with the smallest element. Okay, so here I'm going to use now 1/4, right? Because 1/4 was the smallest element in this group. I guess I was using yellow, which should try to be consistent there. All right. So I'm going to replace everything with the smallest element in its group. Does that make sense so far? Does everyone see what I'm doing? Maybe let me here, if I really want to color code this. Like that. Okay. So what happens? What do you get? Right. And this is always true, right? Why? Because notice that the way that I've grouped them, I've guaranteed that the smallest element, so in general, right? What we're going to have is we're going to have 2k terms of the form 1/2 to the k plus 1. And that's always going to give me 1/2. So now what I have is that the harmonic series is going to be greater than 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2. And that's easy. It should be easy to convince yourself that thing does go off to infinity, right? So what you've done is you've just grouped the terms of the harmonic series in a very clever way to guarantee that, all of those things just look like halves. And so this allows you now to bound the harmonic series below by something which does shoot off to infinity. So does that make sense? Do you see how that works? I think that's a super cool little trick, right? And so now, you get that, like, basically, what do you get? You get that the 2kth term of the harmonic series is always greater than, I don't know, k/2 to the k, something like that, or whatever it is. Like, k times 1/2 or something, k/2. So it certainly converges. What's the exact number? You get something like this. You get like s2 to the k is greater than, k plus 1 over 2, something like this, right? It's probably not exactly what it is, but it's something like that. And so now it clearly goes off to infinity, because as you let k go to infinity, the right-hand side becomes arbitrarily large, right? So that's another proof that the harmonic series diverges that doesn't require you knowing anything about log, right? So let's say, for example, if I started the year with this is the proof I'd have to give you, right? Because we don't have the definition of a logarithm. We don't have integrals. We don't have upper and lower Darboux sums. This is the proof that I would have given you there, is that this thing shoots off to infinity. But so that's a really cool trick. There's a ton of tricks that you can use. There is actually an integral test, which is if your series looks like a function that you can actually integrate, then you can use, it turns out your series converges if and only if your integral converges, which is a crazy thing. And actually, you guys should try and prove that, because you all have the tools to prove that. Okay, so as just kind of like a bonus, I want you to try and figure this one out yourself. Okay, you all can do this, 100%. Every single one of you can do this proof. And do you remember in assignment 10 how you bounded log above and below, right? What did you use? You just used the lower Darboux sum for one and the upper Darboux sum for the other, right? You remember that from assignment 10? Just do exactly the same thing here. Take, basically what you're going to do is you're going to relate the series to the integral just by taking the Darboux sums on, the silly partition, right? Where you take 1, 2, 3, 4 as being your partition points. This is going to allow you to bound the integral in terms of the sum. And so now if the sum converges, you've squeezed theorem your integral sort of thing, right? And so now suddenly you have this like really cool test that tells you about these two things, right? The series and the integral. And so now clearly the harmonic series diverges if you have this test, right? It has to diverge because we know the integral of 1 over x diverges, right? And it gives you other things too, like it gives you 1 over k squared converges. In fact, what you immediately see, and this isn't how we're going to do it, but you immediately see the p-test, right? That the improper integral on the right converges if it's 1 over x to the power of p, right? That converges if p is greater than 1. We immediately get that that's true for series as well. So I'm going to try and prove that directly. Probably on Thursday, we'll do the p-test. But if you have this theorem, you immediately get that the p-test translates over to series as well, right? So I'd say give that a shot if you want. The proof really isn't that long. Like I said, it's basically the same as what you did in assignment 10. Give it a shot, see if you can make it work. Okay. Otherwise, I think, what am I going to do in 3 minutes? I think the answer is nothing. So I think we can call it there today. I think there's lots for you to digest and to think about. Yeah, is there any like obvious exercises? You can just try if you want, write some stuff down. It's like I said, generally it's very hard to find a closed form expression for the partial sums. So there probably isn't a crazy amount that you can do. But one thing you can do if you want, remember when I did this, where is this example? The first example that we did, right? What I did is I just took this telescoping series, did the cross multiplication, gave it a common denominator, and then worked it out. If you want more practice, you can do exactly the same thing. Take a harmonic or take a telescoping series, be creative in how you do it. Take a telescoping series, simplify it, give it a common denominator, and then go ahead and do it as if you didn't know it was a telescoping series. So if you want practice, that's a great way you can do it. You don't just, you don't have to limit yourself to a telescoping series of 2 terms. You can have like a telescoping series of 3 terms where maybe only 1 term is canceled each time you sum, or maybe 2 terms are canceled each time you sum. Playing around with those sorts of examples can be really insightful and really, really good. So if you want practice, do that as well. Otherwise, on Thursday, what we're going to do is I'm going to start proving for you the tests. So p-test, basic convergence, and limit convergence. Basic comparison and limit comparison. If you really want practice too, try and state and prove those theorems yourself. They are exactly the same statement as they are for improper integrals, but you just convert them to sequences, and the proofs are the same as well. Okay, so really, really, really great practice. If you want to see how well you understand the stuff so far, figure out how to state and prove the basic limit, the basic comparison test and the limit comparison test. P-test is harder. If you really want to practice, try and prove the p-test from scratch. P-test is tough, but BCT and LCT are exactly the same as the improper integral proofs. Okay, so that's kind of your homework if you're interested, if you want to give it a try. Otherwise, you have actual homework, right? Whatever. Yeah, that'll finish this off today. So have a good Wednesday, everyone, and I will see you on Thursday.